Swayam Prabha. Digital India. Educated India.
Okay, now let us look at the discrete log and relatives. Okay, so now what I want to do is I want to use cyclic groups, okay, and preferably with prime order. So, it is not always necessary to use prime order, but for simplicity let's assume that. Okay, so let G be a group generation algorithm. So, this is similar to what we had for RSA and factoring, like the modulus generation. So, now we have a group generation algorithm which as usual will take the size of the problem, some n, and it will order a cyclic group of that order, whatever size you told me. I will give you a cyclic group of that order and I will give you a generator for that group. Okay. So, this algorithm takes as input and outputs a description of a cyclic group G of order Q such that the size of Q is n. So, this just means that Q is n bits. This is just size of Q in bits, okay, and a generator G. Okay. So, now we have a way of generating a group, a finite group which is cyclic. It has prime order, let us say. I mean there are other groups which do not have prime order. A very notable example is actually ZP star. So, if P is prime, ZP star has order P minus 1, but this is a very popular group even though the order is not prime. Anyway, let us not whatever, we will see if we need, we will operate at a level of abstraction where we will not get into the particular groups maybe that we use. We will just talk about there being a group, there being an order, and what are the hard problems on that group, right. So, first let us define what is a discrete logarithm. So, discrete logarithm just means that if I give you a random element in this group, okay, I anyway output for you the generator of the group and the order of the group. Okay, now if I give you a random element in this group, then there must be some exponent for the generator, right. So, there will be some x. If I give you a random y in the group, there will be some x such that g to the x is equal to y in the group, right, whatever is the group operation. Is it clear? So, for concreteness, if you want to think of the operation as multiplication, so note that in an abstract group we are not actually defining what the operation is, right. So, a group will just have some operation. It could be something fancy like in elliptic curve groups for instance, but for simplicity if I think of multiplication, then given a generator G, right, if I am given a generator G and I am given some y in this group, right, then there exists some x such that g to the x is equal to y. This is because g is a generator. So, by definition I can use it to generate y, right. So, this x is called the discrete logarithm of y relative to small g. Okay. So, I will write it a little better, maybe a little bit more explicitly. Actually I won't do it. So let us just go with this. So this is just saying that given this generator G and some Y in the group, because of the fact that G is a generator, this means it can generate Y. So this means that there exists some x such that G to the x is Y, okay, and we will just call x as the discrete logarithm. The name is very it's obvious why the name, right. So, it is a logarithm and it is discrete because it takes discrete values. Okay, so, this is the discrete logarithm of y with respect to small g. Okay, so, now so the discrete log experiment you can define similarly as before. So, the discrete log experiment this is once again you run this generation algorithm to get the group, the order and the generator, right. This is the order, this is the generator. Having done this, you choose a uniform y in the group. A, our adversary, is given the group description, the generator, the order and this y, and it outputs some x in ZQ, and output 1 if g of x is equal to y in the group, else output 0. Okay, so, as usual we say that the discrete log problem is hard relative to a given group if for any PPT adversary A given, I am not writing it out in longhand this time, okay. It is exactly as we have written before. So, the discrete logarithm problem is hard relative to a given group generation algorithm if for any PPT algorithm A who is given G, Q and small g the generator as well as a Y, right. So, this is already written here, right. So, what all is A given. So, for any PPT adversary who is given all this, if it outputs an x such that g of x is equal to y, right, then we say that the adversary has won, and the assumption is that the probability that any adversary can do this should be negligible in n. This is the discrete log assumption. Okay, so, in very short I will just say that DL is hard if for all PPT A probability that this experiment outputs 1 is negligible in n, okay, and the DL assumption is that there exists a G, a group generation algorithm for which DL problem is hard. So, I hope that it is clear to everybody what is the difference between, there is an experiment, there is a definition of hardness and then there is an assumption, and this is it might seem like a little bit of overkill, but we need this formalism because later on as things get more complex, well, I mean even in the simple case you need the formalism to argue anything properly, and it is particularly important as things get more complex. So, any questions? Let me, while I am on this, let me also very quickly define these Diffie-Hellman problems. Okay, so, I will not spend too much time defining them in detail, at least right now. So, there is a computational version. So, this will be called computational Diffie-Hellman, and there is a decisional version. Okay, so, this will call decisional Diffie-Hellman. And yeah, so let us define. So, we consider the group G with the generator G as before. Okay, G is again a cyclic group. So, just as in the previous slide, and now we will define DH Diffie-Hellman G of some H1 H2, right, as G to the log H1 times log H2. So, what this means is that if H1 is G to the x1 and H2 is G to the x2, then DHG of H1 H2 is nothing but G to the x1 x2. In particular, this is H1 to the x2 and this is H2 to the x1. So, CDH problem is to compute DHG H1 H2 for uniform H1 and H2. Okay, and DDH is simply to distinguish DHG H1 H2 from uniform. Okay, so let us look at it more carefully. Basically, we are still in our cyclic group, okay, with generator G. Now, what am I saying? If I give you G to the x1 and G to the x2, it is hard for me to compute G to the x1 x2. This is the computational Diffie-Hellman assumption, okay, that if I give you a random H1 which is G to the x1 and a random H2 which is G to the x2, then the computational Diffie-Hellman assumption is that it is hard for me to compute G to the x1 x2. Note that if discrete log were easy, this would be easy, because if I have G to the x1 and G to the x2, if I could compute x1 or x2 from that, then I can compute G to the x1 x2, no problem. So, if discrete log is easy, this is definitely easy. As usual, the other direction will not necessarily hold. And the decision Diffie-Hellman problem is going a step further. It is saying not only cannot you compute, moreover, to a computationally bounded, basically to a PPT adversary or algorithm A, G to the x1 x2 actually is indistinguishable from uniform. So, if H1 and H2 were chosen uniformly, then DH of H1 comma H2, which we defined over here, right. This actually for uniform H1 and H2, the DDH assumption is saying that this distribution is indistinguishable from uniform. So, if I am giving you some samples that are just on one hand I just sample them uniformly from the group, and on the other hand I compute them like this. The DDH assumption is saying I cannot tell the difference if I am bounded by polynomial time. Of course, again if I have unbounded time, I can solve the discrete log problem and I can check if this relation is holding. So, it is, you see the flavor, right. So, there is an algebraic structure. The hardness is coming from the idea that I cannot discern this structure, much less compute something. I cannot even tell if this is structured or if this is uniform. And what does what do these problems give us? So, you know, one very immediate thing that they give us is key exchange. So, the DDH assumption, the decision Diffie-Hellman assumption gives us key exchange, and this is something which I am very fond of talking about. If you remember, in the very first class I talked about it, right. So, all of us are sitting in this crowded room, and let us say that I want to speak privately to one person without ever leaving the room, without exchanging any private messages. There is a way for me to establish a secret key and subsequently communicate in private, all of this while sitting here in this room with everybody hearing everything, right. And how is this? So, if I have two users A and B, right, I sample x1, so in ZQ star, right, you sample x2, okay. I announce, or you know, I communicate G to the x1, right, you communicate G to the x2. Now, given G to the x2, I can raise this to the x1, and given G to the x1, you can raise this to x2, so that both of us will get G to the x1 x2, and the DDH problem tells us that this is actually indistinguishable from uniform.
So even the eavesdropper can't actually find.
Not only can the eavesdropper not find anything, in fact the eavesdropper according to the DDH assumption learns nothing. So, what does the eavesdropper see, right? The eavesdropper cannot see inside our heads, so it can only see these two. And this is exactly the situation that the DDH assumption is handling. Given G to the x1 and G to the x2, I cannot compute G to the x1 x2, and I cannot even distinguish it from uniform. Okay, so that means that in the view of the eavesdropper, what she sees is G to the x1 and G to the x2, right. And now G to the x1 x2 is actually uniform, right. That means that it is indistinguishable from another random element in the group. So, she learnt exactly nothing about the secret key that was agreed upon. Now, I want to make a couple of quick remarks right before we stop for today. So, one quick remark is that the discrete log problem actually gives a one way permutation. I hope everyone can see this. Okay, so, since we took the cyclic group, right, we got a permutation, right. So, if I define my function as f of x equals G to the x in the group, okay, then it is clear that this function is going from G to G, right. And because small g is a generator, this is going to be a permutation. For every y in G, there will be an x such that G to the x is equal to y. Okay, so, this gives us a one way permutation. The discrete log assumption tells us that given G to the x, I cannot compute x. So, this is the one way property, and additionally it is a permutation, not just a function. So, this gives us a one way permutation. And again, I did not very formally define this one way permutation, one way function. I am actually unsure if we really require to. So, maybe we will keep it, you know, just a little bit informal the way we have done it right now. I mean, it is not like there is anything very complicated about it, just that we will have to go through some definitions. So, the idea will just be that, you know, I will have to, like if I want to define a one way permutation, I will need to define like a key generation algorithm, or you know generally a setup algorithm which outputs the group and the order and the generator, right. Then I will have to define an evaluate algorithm, right. In the case of a trapdoor permutation, I will have to define an invert algorithm, and I will have to define the security which will say that so long as you generated things in the proper way, for any PPT adversary the probability that it can compute the inverse is negligible, something like that. But thinking ahead about the course, we will not really need at least these things like this one way function, one way permutation, TDP, we will not be exactly using them. So, maybe keeping it just a little bit at a high level is alright for us right now. Okay, so I do not want to spend too much more time on this. So, what did we see today? So, we saw factoring, we saw RSA, we saw discrete log, we saw CDH and DDH. Okay, we saw that from factoring we get a one way function, from discrete log we get a one way permutation, from RSA we get a trapdoor permutation. Remind yourselves why this is. Okay, so that is because I defined my function f of x as x to the e mod n, right, and given a d such that e times d is 1 mod phi n, I can raise this to the d and recover the original x. Okay, so this is a trapdoor permutation, and then we defined more advanced sort of problems like the computational and the decisional Diffie-Hellman problems. From this I already showed you one very nice thing, again I showed it more at an intuitive level. This is the key exchange. So, this is also something where if we need to explore it more formally, let us do it in the homework. So, basically what you would need to do is just define what the security game should look like. So, basically for a passive attacker who only sees the messages that are being sent, we should be able to argue that the key that is generated is completely random from that person's view, and this is given directly by the decisional Diffie-Hellman assumption. Okay, so yeah, so we will just keep this informal. What we will do is next time we will define public key encryption. Okay, so rather than defining these smaller things more formally, let us go directly to public key encryption, that we will define formally. We will define the algorithms and the security game, and we will show how to build it from DDH and factoring. Okay, so that will give us like a very concrete scheme which later we can quantumly break. Okay, and these schemes are in fact used all over the place. So, it is good to see like this will be what will be broken. Alright, so we are over time, thank you. Yeah, good question. So, the question is that in RSA or factoring even, why use only 2 prime numbers, why not use many? So, the answer is that if you use many, right, then either your overall modulus capital N will keep growing, right. If I use small n times small n times small n, then this will be 3n bits in the end, right. If I stick with capital N as my upper bound, then splitting it into 3 will make the problem easier, right. So, there is no advantage in some sense to using more factors because no. So, very good. So, I like the way you are thinking. The question is that since these are so popular in practice, maybe there are particular prime numbers that people always use, and then this becomes a problem. So, let me give 2 answers to that. So, first of all, having 3 primes will not help you with that problem, right. Neither will having 4 or 5 or 6 or 10, right, that will not help you with the problem. What will help you with this problem is just like how I said, no one can help you if you use the same password, no one can help you if you use the same primes or if you choose badly used primes. So, there is a hygiene in how you select these prime numbers, right, and you are pretty much supposed to follow that. So, if you do not sample your primes randomly, right, if you use whatever somebody else used or something like that, then the security of your system will get compromised, and that is something which Actually, these are questions that arise in security beyond cryptography. You know, so cryptography will tell you what is the way to do it and mathematically what will work. But beyond that, you know, are those best practices being followed or not, right? And there will be other issues also. But this kind of an issue will have to be handled by the implementer. Does that answer the question? Yeah, very good question.